SwayamPrabha. Digital India. Educated India.
So let's continue with our discussion on the Routh's criteria. So yesterday we started off with the question as to how one could obtain the distribution of roots of a polynomial. Okay, so that's the question we asked ourselves, and we figured out that we can construct the Routh's array and then check out the number of sign changes in the first column of the Routh's array, right? And the way in which it can be used for control system design is to essentially check for what values of controller parameters the system, closed loop system would become stable. Okay, so that's what we did yesterday. So we formed the Routh's array for the closed loop characteristic polynomial and then figured out the feasible regions of the controller gains, right? We just did one example. So today I'm going to do a few more examples, just to point out some special cases that may prop up with the construction of the Routh's array and then how to handle them. Okay, so in general we can use the Routh's criteria to figure out the distribution of roots of a polynomial, right? So that's what it's about, right? So let's consider a couple of special cases. Okay, so the first case is when the first element in any row of the Routh's array is 0, okay, with the other remaining elements or entries being non-zero. Okay. Okay, so that's the first case that we would be studying. Okay, so as an example, to understand this case better, let's consider the polynomial, the following polynomial: s power 4 plus 3s cube plus 3s squared plus 3s plus 2. Okay, let's consider this polynomial. Okay, so once again, of course, since please note that here I am trying to figure out the distribution of roots, right? So anyway, to begin with, we can observe that all coefficients are non-zero and of the same sign, right? So at least that is satisfied in this particular polynomial. So let's construct the Routh's array. See, if you want to figure out the distribution of roots, you can continue even if that necessary condition is not satisfied, right? That is the necessary condition for stability. Okay, once you look at the closed loop characteristic polynomial. Okay, but in general, as I told you, Routh's criteria can be used to figure out the distribution of roots of a given polynomial, right? So you can continue even if some entries are negative to figure out, how the polynomial's roots are distributed. Okay, so but anyway, let's continue and construct the Routh's array. So we write s power 4, s power 3, s squared, s power 1 and s power 0, and we start filling in the values, right? So the entries are going to be 1, 3, 3, 3 and 2. So what's going to come in the s squared row? So minus 2. So 3 times 3 is 9, 9 minus 3 is 6, 6 divided by 3 is 2, right? So similarly this entry will be 3 times 2 minus 1 multiplied by a null entry divided by 3, I will get 2, right? Then that's about it, right? So I go to the s power 1 row. So in the s power 1 row we have 2 times 3 minus 3 times 2, that's going to be 0, right? So you see that 0 by 2 I will get a 0, right? So you see that of course in the s power 1 row this is the only entry, but you see that the first entry is a 0 entry. Okay, then what do we do? Okay, the procedure to follow is the following. Okay, so replace the 0 entry with a small positive real number epsilon, okay, and continue the process. Okay, and from here, once you continue this process, if there is a sign change, okay, from the entry above epsilon in the first column of the Routh's array to the entry below epsilon, okay, then there are roots, okay, in general, okay, in the RHP. Okay, so that is the implication. Okay, if there is a sign change below and from the entry above epsilon, let's say if the entry above epsilon is positive and if the entry below epsilon is negative, right, then there are roots in the right of plane. If not, that means that if there is no sign change between the from the entry above epsilon to the entry below epsilon, then there is a pair of roots on the j omega axis, okay, or the imaginary axis. Okay, so that's what it implies. Okay, so let me repeat what we are doing as a first special case. Let's say you construct the Routh's array, like at some point, okay, you come to a scenario where the first element in the Routh's in any row of the Routh's array happens to be 0, with all other potential non-zero elements being non-zero, okay, one or more, okay, at least one element should be non-zero. Okay, then what you do is that, like, you replace that 0 element, which is the first entry in that row, with a small number epsilon. Why should I do that? Because if I want to continue and calculate the s power 0 row, you see that I have a problem, right? Because if I do 0 times 2 minus 2 times null entry by 0, I get 0 by 0, right? So I don't go anywhere, right? So what we do is that, like, we replace this 0 by a small positive real number epsilon and continue the calculation. Okay, let's see what happens here. Okay, so what we are going to do is that, like, we are going to replace this 0 with a small positive number, positive real number epsilon. So then what happens? Let's continue the calculation. Okay, so we get 2 epsilon minus 2 times null entry, which is 2 epsilon, divided by epsilon. So what do we get? 2, right? So if you look at the entry above epsilon, that is this. If you look at the entry below epsilon, which is this, right? Is there a sign change in the from the entry above epsilon to the one below epsilon? No. So this, we can observe that there is no sign change from the entry above epsilon to the one below epsilon in the first column of the Routh's array. So what does this imply? This implies that there is a pair of roots. Of course, there are no other sign changes also, right? see if you look at the first column itself, right, of the Routh's array, there are no further sign changes also, right. There is only one 0 entry which we have solved by, which we are addressed by replacing with epsilon and continuing the calculation. So this leads us to conclude that there is a pair of roots on the imaginary axis. Okay, so that is the conclusion which one can draw. Okay, and it so turns out that if you calculate the roots of this polynomial, the roots are -1, -2 and plus or minus j. Okay, so those are the roots of this polynomial. Okay, so you can see that out of the 4 roots, there are 2 roots on the j omega axis, the remaining 2 roots are in the left half plane, right. So without even calculating, solving for the polynomial, like polynomial's roots, like we can get the distribution of roots, right. So that's what we are interested in to begin with, right. So that's the first special case. Okay, so I hope it's clear to everyone what we did. So just to re-emphasize this special case, let's do one more example, wherein like we consider d of s to be just to convey the point, s cube minus 3s plus 2. Of course, you see that not all the coefficients are 0 and of the same sign, but that's fine, right. So right now we want to find out the distribution of roots. So let's carry out the construction of the Routh's array. So s cube, s squared, s power 1, s power 0. So I am going to get the entries as 1, 0, minus 3 and 2. Okay, so those will be my entries in the Routh's array, right, is it not, when I write down the coefficients, because s squared coefficient is 0. So that is what we have. So immediately we see that the first entry in a row, in the s squared row is 0, but there are other non-zero entries, right, namely in this case there is a non-zero entry 2. So what do? We replace this with a small positive number epsilon and continue. So then what will I get? I will get minus 3 epsilon minus 2 by epsilon, right. So that is what I will have. So I will have minus 3 epsilon minus 2 divided by epsilon, right. So that is what I will have in the s power n 1 row, right. How do I get this? I multiply epsilon and minus 3, 2 and 1, subtract it and then divide by epsilon. Okay. Then what will I get for the s power 0 row? I will just get 2, right, because I need to multiply minus 3 epsilon minus 2 by epsilon with 2, epsilon with nothing, so that won't change the result in the numerator, and divide by minus 3 epsilon minus 2 by epsilon. So I will just be left with 2. Okay. Now if you look at the elements below and above epsilon, okay, the element below epsilon has a positive sign. What can you say about the element, the element above epsilon has a positive sign. What can you say about the sign of the element below epsilon? It's negative, right, because you can see that epsilon is a positive number, right. So it is going to tend to a negative number. So now one can observe that there is a sign change below and above epsilon. So that we need to count as one sign change. Okay. See, we need to count the number of sign changes, right. Then from s power 1 row to s power 0 row in the first column, is there another sign change? Yes, there is, right, because this is also another sign change, right, because in the s power 0 row we have plus 2, right. So there are 2 sign changes. So this implies that there are 2 sign changes. So this implies that there are 2 roots in the right half plane, of course with the remaining root in the left half plane, right. So that is the conclusion we can draw here, and it so turns out that the roots of this equation are minus 2, 1 and 1. Okay. So those are the roots of this equation. Okay. You can factorize this polynomial as s minus 1 whole square times s plus 2. Okay. You can try it out. Okay. So you see that those will be the roots, right. So that's what we could figure out, right. So that's the first special case. Okay. So when the first element in any row happens to be 0, with other elements being non-zero. Yes?
I mean, the definition says first element of any row, but it's always the first column.
First entry, yeah.
Column as such?
What did I write down? Okay, 1 minute. The first element in any row of the Routh array, right? Because see, we need to always divide by the first element, right? Right. So, see, not the first column. The first element in any row of the Routh array. Okay. Obviously, that will appear in the first column, right? If there were a 0, this special case deals with the first any entry in the first column of the Routh array being 0, but you have to look at the row, right? Because I have to go from one row to another, right? See, if I am filling the Routh array row wise, right? For any row, I look at the 2 rows immediately above it, right? So if I have a 0 entry, I cannot proceed because I need to divide by the first element in the preceding row. That's how the calculation happens, right? So I cannot proceed. So that's why we do this.
And these 2 points here, the converse of them applies, that is, if there's a pair of roots on the JW axis, that means that.
Yeah, you can figure it out by using this method. Okay. Yeah.
No, I'm saying the converse of the point 2 especially.
What's that?
If there is a pair of roots on the JW axis, G omega axis, if there is, does that mean that there's
Why don't you try it out? Okay, you construct an example and let me know. Okay. So his question is that, like, what will happen if is it basically the question, if I want to put it in a different way, like, is this necessary or sufficient or necessary and sufficient, right? So why don't you check out the converse as a homework? I think I gave you some homework yesterday also, right? I think that was a pretty simple one, right? So for getting the quadratic necessary and sufficient for the quadratic polynomial, right? So please check out the converse, right? Construct an example, construct many examples as you can, right? So then you go and check out whether this really happens, right, in the Routh array, or if it happens in the Routh array, you can interpret this condition, right? But it need not happen always, right? So that's a question which you need to answer. I will just give you a hint, okay? So if you essentially use MATLAB, okay? So I would essentially you use the command poly, okay, to essentially get the coefficients of any polynomial once you give the roots. See, for example, I want to essentially get the polynomial corresponding for which the roots will be -2, 1, 1. Okay. So then what I do is that I go to MATLAB, I just type poly and -2 space 1 space 1. Okay. So this will give me the coefficients in the sequence. Okay. This will give me the answer as 1, 0, -3, 2. Okay. So that will help you in constructing polynomials. Okay. So that you can verify it. So if I'm given a polynomial, you use the roots command, right, to get the roots. If you are given the roots and you want to find the coefficients of the corresponding polynomial, use the poly command. Okay. This can help you in playing around and like figuring out various special cases. Okay. Please try it out. Yeah, sure.
Both cases are possible in some case. Is there a possibility they have pair roots on the JW axis and in the other stream?
Why don't you try? Okay, just construct an example where you have, let's say, roots on the j omega axis and also roots in the right of plane, and then try it out. Let's see what happens. Okay, yeah.
So the coefficient of S square is 0, so we can easily rule out whether necessary.
Okay, good point. Once again, it depends on the purpose. Okay, the question here, what we are asking is, how do we, can we get the distribution of roots, right? Yes, you are correct. That's why I gave a preemptive statement saying that, look, the necessary condition per se is not satisfied. That is a necessary condition for all roots to lie in the left of plane. Here I am not asking you the question whether all roots are lying in the left of plane. We are just seeing, like whether we can get the distribution of the roots, right? So that is the objective here. That's a good point. I hope everyone got it, right? So if you give this polynomial to me as a denominator polynomial of a transfer function, just by observation I will say that, look, the system is unstable, right? I don't even need to construct the Routh array, right? Because I can see that the necessary condition is violated. That is, all coefficients must be non-zero and of the same sign, right? But then our task is to here, you know, like just construct the routes array and learn. Okay, so that is the idea, right? Okay.